And then that should be that. And so while that is going live, thank you very much for coming along to .NET Knots. It's raining here. Well, it's kind of just miserable generally because it's like it's autumn. Oh, there's me because that's working. You can hear me. That's good. Mute that. Yes, before we get going, we do have a code of conduct. There's lots of words there, but the one on the bottom right, be kind and considerate to others, really sums it all up. So please do that. If anybody feels like they've been made to feel uncomfortable, then come see me or one of the BGSS people if you're here. Send me a direct message on Zoom if you're not right here, and then or Connell, in fact, and we'll deal with that promptly and keep you up to date on what that process looks like. Thanks very much to our sponsors. BGSS are putting us up here and providing us with the alcoholic drinks for the evening, so thank you to them. Rebel Recruiters, who are an awesome recruitment company based in Nottingham. They're really good. They're paying for our pizza if you're in person. Sorry, you folks. And soft drinks, so thanks to them. My company, my consultancy, still running in the background, PJG Creations. They're sponsoring all of everything else, aside from what JetBrains are sponsoring, which I'll talk about shortly. If you tweet rather on the hashtag .NETKnots, then there's a very good possibility that you'll win a JetBrains license, because I've got a few of those I need to give away. So if you don't know what JetBrains do, they make developer tools for developers. So things like ReSharper, WebStorm, PHPStorm, IntelliJ, all of those good things. PyCharm, in fact, I've been looking at recently. That sort of stuff. So do tweet on the hashtag .NETKnots, and thanks to them for their kindness in that regard. There's at least 2 MVPs here. In fact, our speaker and myself are Microsoft MVPs. Are you an MVP now, Connell? Can't remember. I think we talk about this every time, and I think, well, why aren't you?
Yeah, no, not me.
Yeah, no, it'll happen. We'll sort that out. Either way, if you'd like to find out a little bit more about what that means, then you can approach me or indeed Mr. Whitney, and we'll guide you through what that process looks like. Well worth getting involved if the community is something that you're passionate about. Tonight, we've got David Whitley talking about how we can render 3D worlds in C#. What got me was he simply mentioned the word Wolfenstein in the talk description, and that was enough for me. So, yeah, I'm looking forward to that one. Coming up, I think we may have sorted out that Connell and somebody else may well be speaking in October, but we're yet to confirm that. But at the moment, so that's TBA for next month on the 28th, I think. Coming up a week on Thursday, we've got Simon Prickett talking about Raspberry Pi sensors and CrateDB at Knots IoT, so that should be a good one. And then if robotics and automation is your thing, the day before that, so a week on Wednesday, across in Loughborough for Lati, we've got Craig Lawson-Devine and Will Haynes talking about exploring autonomous vehicle development with ROS and LiDAR and the benefits of emulation. So those should be good as well. And with that, I'll stop waffling on. I'll stop sharing my screen and we'll let David Whitney. Oh, disappointing. Yeah, nearly. I can do that. I've got a song and a dance I can do if you like. Yeah, apologies for that. That's probably something I should have said before we got there. So I'm going to stop sharing, which is always good. And while our speaker hooks himself up to the Wi-Fi. Velcro, like it. Very good. And then we'll let you in. I think it's just, what is it, BGSS guest or something, isn't it? Yes. Mm-hmm. Yep. I would say we'll cut this out of the YouTube version, but I'm a bit too lazy for doing that. Yeah, I think you're right. Yeah, I agree.
I love the live TV vibes you get from having a live.
Yes. Yeah. Accidentally cutting in the outtake of somebody trying to do a piece and getting it wrong and then swearing at the end of it, just like Formula One. There's David Whitney. Right. And then I need to make you a co-host so that you can share your screen. Once you're in. There we go. make you a co-host. So it should do that. There
Yeah.
you go. And then you should be able to share your screen. Right, I'm going to mute myself as well for that same reason.
Okay. This is challenging. Perfect. There we go. Action packed. Now let's see if this works.
See that cable behind you? That'll
Yeah.
just throw to one side. Matt.
Oh, hybrid events. Gotta love them.
Yeah.
Right. Everyone online gets the excellent down the nose angle. 10 out of 10. 10 out of 10. And then we hope we can extend. We can extend. Keep changes. Perfect. And then we're going to share a screen. We get to narrate this in slow motion, so I know what I'm doing. It's wonderful. Yeah. You see, I don't use Zoom, and they move my cheese every time I see it. Okay, that's screen 2. Wonderful. And then we find the slide deck and we present it. Okay, thumbs up online. You got it. I see a bit of thumbs up. Perfect.
Good work.
I think that was an interesting exercise. And I probably want to hide that bar on that screen for everybody else. Go away. Go away.
Ah,
You hit it enough and it moves. Awesome. Okay. Hi, that was a very, very interesting opening. I'm going to talk about rendering 3D worlds, but actually, anyone did an art degree here at all? No, brilliant, because you're about to learn about the history of perspective and traditional fine art and painting. That's really what this talk's about, with a bit of programming in it. Any questions? I'll take them at the end, unless they're about maths, in which case I'll probably look them up on Wikipedia in front of you, because I'm not a maths expert. This slide is pretty boring when I'm standing here. So I'm a mostly software consultant. Also, I work at a company called New Day as their director of software architecture. I spent 15 years teaching people, mentoring them, teaching TDD, and mostly with silly fancy job titles, but most of the time I really just like making stuff. Like, I really got into programming because making stuff is fun. I've written a couple of kids' books about computer programming, the very, very innovatively titled Get Coding 1 and 2, available in all good bookstores. I can get my 15 pence of royalties. And recently I built a 3D renderer in C#, mostly just to see if I could, honestly. Now, the first question that everyone always asks is like, why would you ever really do that? Like, there's lots of 3D renderers that already exist. And the truth is, it was all a bit pointless, really. But that's why. So I actually built this in 2020 during lockdown, and I think there are a lot of different answers to the question why, when you do something like build software that absolutely doesn't need to be built by anybody. Mostly, I just wanted to see if I could. Not very good at maths, so I was curious to see if I could work it out. I feel like so often we're forced to work in these bleak, corporate, brutalistic hellholes where only things that have to get rendered into reality for money by 100 clients and megacorps get to exist. So this was really the opposite of it. 3D engines exist, and you should probably use those rather than building them yourself for the most part. But, you know, if you want to build a game, the truth is, probably don't do what I did in this talk. Go use Unity or Godot or whatever's trendy this week. But if you want to do silly things and see what you're capable of, this is the kind of absolutely weird and wild shit that keeps me actually still wanting to write computer software rather than attending meetings. So I want to caveat a few things about history before I get into the meat of this talk. So in this talk, we're going to talk about technological advancement from a period where things were all being invented at the same time. So lots of different games were kind of coming out and pushing the boundaries of 3D and 2D tech. So for every game I mention here, you can probably gotcha me with like, didn't you know there was this one game that did half of that thing 6 months earlier? Yes, probably. So don't feel slighted if I don't mention the favorite thing that you had or that one game that made you feel good as a kid. I'm sure it's awesome and probably quite important. So before we do this deep dive into this kind of history of 3D graphics, I think it's important to understand what three-dimensional images means in the first place, like this idea of 3D. Now, obviously, your computer monitors are all 2D. Well, I guess they have volume in the real world, but the image on them are two-dimensional. So they literally have two axes, an X and a Y axis, and they render flat images. So when you try and draw by hand something that looks 3D in a 2D space, it often looks really strange and wrong, kind of like this. So this screenshot, anyone know the game? Rampage. Classic Amiga, I think, Rampage originally. So it's clearly a 2D image, but what that is depicting, what it's representing, is also obviously a 3D space. Like we know that's a 2D rendering of a cityscape. It's not 3D, it's definitely not 3D, it's not even kind of proto 3D. There are only two planes, left to right, up and down in this particular image. So making a two-dimensional image three-dimensional is not about the fidelity of the image at all, but in fact, how you capture perspective. And perspective is a traditional art technique, often kind of credited to a bunch of people. It was actually first described in the 15th century. So there's this guy called Leon Battista Alberti, who wrote a book called On Painting in the year 1435, and that's the origin of the notion of perspective. So if you've ever looked at really, really old paintings in museums, you'll notice that there's like this era of art where it goes from everything looking completely shite and nobody knows how to do proportionality to, oh, look, all of a sudden we've kind of got perspective right, and there's things in the distance and they seem realistic. And that was because of the works around the 14th century to invent the notion of perspective. So the idea behind most perspective is you plot a horizon or a vanishing point, and then you position elements along that horizon and vanishing point to simulate depth. So linear perspective is just one kind of perspective that you'll see all the time. Now, there's a really good diagram here. So a projection is a graphical technique that maps three-dimensional points into two-dimensional space. And there's some maths that you can run depending on the kind of perspective to represent things differently. And projections come in lots of different forms. Actually, different kinds of projections are differently useful. But the key is that a projection is defined by where the focal point is and how many focal points are in the image and where they are placed. So accurate perspective projections are what makes something look 3D in a 2D space. That's why Rampage doesn't look 3D, because there is no focal point. So one point perspective is the one you'll probably be most familiar with, because it's the first person shooter camera on your face perspective, where there's a single focal point where a lens is and everything kind of goes off into the distance from there. Now, early games, by comparison, this was computationally quite difficult to do. So early games tended to use orthographic perspectives, or for instance, to render isometric views into 2D space. Now, we still consider these 2D games by today's standards. We're not doing any 3D depth calculations. And that's exactly why isometric perspectives were useful in those early games, because they were computationally super, super cheap. And the reason is, in an isometric perspective, images don't scale when they're further away. So you can represent things at different distances without having to scale the bitmaps at all. Super, super computationally efficient. Now, it's worth remembering that when we talk about 3D today, that what we're referring to is polygonal 3D most of the time. And actually, gaming has a history of pre-polygonal 3D. It's a mouthful. And it's worth considering that as part of the journey that we took towards where we are today, where everything kind of uses similar rendering techniques. So this is a recent-ish now screenshot from the very first Unreal Engine 5 demo. So this came out in 2021. And you kind of really have to marvel at all of the stuff in this thing. Like, it's so beautiful. Like, the image fidelity here is incredible, actually. So there are literally billions of polygons in this image, millions on each rock, because it's using Epic's new, I forget the name of it, mega polygon technology. We're going to go with it. It's not the technical name. Nanite, that's what it's called. And all of these textures are 4K scanned text, they call it something, photogrammetry, mapped onto those billions of polygons. And on top of that, you've got modeled real-time ray tracing, bounce lighting, reflection, particle effects, material simulations. Like, the amount of systemic stuff that's in there is all implemented in pixel shaders on specialist GPUs that crunch all the maths. Modern 3D is like 3 decades of work to get us to this point. But actually, to really appreciate modern 3D, we should probably look at where we started, because when you want to write your own thing, you kind of have to approach it from first principles. And I want to talk about a few things that are 3D that you might not have thought were 3D along the way. So on the left here, we have Tempest, and on the right, we have Maze War. Now, long before general purpose 3D, so these both came out in the 70s, we had what appeared to be kind of 3D graphics using vector-based line drawing techniques. Now, hopefully this kind of challenges the idea a little bit of what 3D really means, because you could argue that that screenshot on the right kind of looks a little bit like a 3D world rendered in traditional polygon ways. So that Maze War screenshot was technically the first ever 3D first-person shooter. So that's 1973, and it was written on a PDS-1 computer. And those polygons didn't exist in the game code at all. They were the result of drawing operations on a pre-rasterization vector monitor, where there wasn't a fixed resolution or bitmap, so kind of like a heartbeat graph on medical equipment. So vector monitors were not divided into pixels at all. So they're basically fancy oscilloscopes. Now, this was a trend that actually continued into the 80s. So maybe some of you might have seen this Star Wars game here. This was like the original Star Wars arcade game. So the way this works is the surface of the vector display is a single layer of phosphor, and it emits light. And then wherever the photon gun hits, you just draw single points in. So it meant that if programmers were particularly creative, they could write drawing routines that would draw triangles and shapes in front of them, kind of like a piece of graph paper with a ruler and a pencil. So games like Tempest and Asteroid and that early Star Wars arcade game, and interestingly, games consoles like the Vectrex, if you've ever heard of that very old console. It's interesting because no one ever had one. Used vector-based games, and they were kind of a natural evolution from those original computer model games like Tennis for Two, the first computer game, which also was played on an oscilloscope display. So it wasn't really a leap to get from really, really early games to kind of this pseudo 3D. Now, the really interesting thing about the Vectrex, the home console that was based on this, it was a self-contained screen and video game console. It was born from engineers at Smith Engineering who had a surplus stock of oscilloscopes. So the reason that not many people had a Vectrex is because they didn't make many of them, because they were an exercise to shift all this spare stock. So they made a video game console kind of by accident. And there was only ever one run. So they're super expensive collector's items today as a result. So then during the 70s and 80s, there was this broad shift towards raster graphics displays. So when compared to vector displays, where you could draw anything anywhere, raster displays use bitmap graphics, so super standard, very similar to monitors you have today. So what that means is that the display itself is divided into pixels, usually directly mapped to an area in memory on these early pieces of hardware. And rather than an effectively infinite resolution of vector displays, where you could shoot the phosphor, you could draw, raster displays worked at fixed resolutions, And you've all used them, and you're using them now on your mobile phone, and nothing has changed since then, basically. So raster displays provided like a really nice level of hardware abstraction over the low-level drawing of vector displays. So much easier to program for these things because you're just painting on a piece of graph paper. Now, vector displays, conversely, had to repeatedly redraw all their operations every refresh cycle to make sure the image stayed on the screen. Whereas raster displays had fixed refresh rates, fixed resolutions, and were really easy to bitmap. Now, even though raster displays were kind of common going all the way back to 1972, so Pong itself was a raster display, over time, the vector displays became less and less common because the arcade industry realized they could write more effective code. Basically, it was much cheaper to build hardware for raster displays. So from basically the 1980s forwards, vector displays fell away, other than a couple of exceptions like the Star Wars game on the previous slide, that I think was 1982. So the games in the 80s that featured 3D often used artistic technique to simulate 3D, which was really just a raster graphics approach to the line drawing in 3D that we talked about earlier, just this time in higher fidelity. So occasionally, in the case of the Atari's iRobot game, which is top left here, specialized hardware was also actually built into the arcade cabinet so they could support drawing really primitive polygons early. So this is technically real 3D, unaccelerated, well, I suppose 3D accelerated with a specialist chip, which you kind of look at as the precursor of some of the stuff that happened in gaming consoles in about 10 years after that. So yeah, pictured here, we have Atari's iRobot with the 3D coprocessor, we have Falcon, and then we have LucasArts Rescue on Fractalis, which I think is this guy down here. So, and then there's this era, which looking around the rough age of people in this room is probably approaching contemporary or thereabouts. So Sega brought out what they called the Superscaler series of arcade machines. So they powered games like Space Harrier and Afterburner. And when you look at them here, you can kind of see how they're all effectively using the same game engine, even though game engines didn't exist at this time. So Sega had become really good at sprite-based pixel art in arcade games. They had a reputation for making these gorgeous, high-color sprites. And they started on this journey towards what was eventually going to become texture-mapped 3D by implementing hardware sprite scaling to simulate perspective. So really what this arcade board was really good at is just that real fast resizing of rasters, which kind of solved the problem of prior generations using isometric rendering, because that was an expensive thing to do. So they built special hardware for it. So they introduced the Sega Superscaler, originally with Hang-On, which is this game down here, in 1985. So the designer of it, Yu Suzuki, was quoted as saying that the Superscaler games were designed as 3D games that simulated using sprite scaling to simulate the look of texture-mapped 3D. And he did it because it looked more impressive than what they were capable of with early polygon crunching, because the Mets coprocessors were not fast enough to do anything else. Now, in fact, Superscaler technology was so influential that, well, Nintendo ripped it off. So this is the famous Nintendo Mode 7 graphics. So this was a specific, it's called Mode 7 because the Super Nintendo had a number of different graphics modes. And Mode 7 was the one where you could scale bitmaps, right? And all of these games use that same technique of kind of pitching and scaling and distorting a bitmap to simulate 3D. This was the foundation of Super Mario Kart, F-Zero, which was a launch title on the Super Nintendo, Pilot Wings, and countless other games. Now, in fact, Sega was so good at this, and they were so enamored by their 2D sprite mapping in the arcade boards, that it actually formed the foundation of the Sega Saturn console, famously. So the Sega Saturn was actually very similar to those Superscaler boards. So there's a really great YouTube channel called Digital Foundry, who did a wonderful retrospective on the original Tomb Raider game. And they use an emulator to unskew the Saturn's texture-mapped quads, because the Saturn was weird in that everything was called a quad, because they didn't use polygons, they just had bitmaps they stitched together as if texturing a surface. So you can see in the top screenshot here, when they took off that hardware transformation, they disabled the feature in the emulator that's what Tomb Raider looks like for that same screenshot at the bottom. Super, super interesting. Ironically, this gave the Sega Saturn a reputation for being really hard to program for because people were expecting more traditional polygon-based 3D at that time. And it's probably the reason that Sony won that initial console war with Sega, because they were a bit cheaper as well. So in the early 90s, there was this kind of slow, lumbering lurch towards true polygonal 3D that wasn't just people basically fucking around with bitmaps and skewing them a little bit to pretend. So we've got some cool, but admittedly very rough early 3D that came out in that time. So all the way until the early 90s, basically our hardware was not good enough to do high poly 3D. So everything kind of looked like boxes. And that means kind of the 3D hardware at the time could only really cope with hundreds of triangles of painted graphics at the time. The engines were slow, and honestly, the art style that was possible from this kind of stuff was pretty janky. So a lot of early 3D really, really has aged badly. I remember when I was a kid, there was like this TV show set in like a VR world, and I swear there was like 20 polygons on the screen at any one time, and they had them in some weird kind of hamster ball contraption, and that must have been 1993, 1994. This stuff really hasn't aged very well at all, to be honest. And, in fact, given the relative quality of true 3D in the early 90s, you can kind of understand where Sega were coming from with their like quads going really fast where they could craft pixel art, because they were really, really good at making those kinds of games, and they just really couldn't make this stuff run fast at all. So that said, Sega themselves are one of the pioneers at true 3D. So Virtua Racing, the middle here, was August of 1992. And it was initially a proof of concept application to exercise their, at the time, new 3D graphics platform, the Sega Model 1 arcade board. So all of these games were basically between the Sega Model 1 and the Model 2 arcade machines, which were what they followed up the Super Scaler with. Now, the late 80s had seen a few polygonal titles in the arcade, so Atari and Namco built a couple, but nothing that could run as fast as this stuff, because this stuff was running at kind of 30 frames a second or so. It felt a bit like a modern game. So they followed up Virtua Racing with Virtua Fighter, two very, very big hits. But you'll notice the interesting thing about both of these, no texture mapping at all, just flat colors. So there were plenty of games that were reaching for real 3D at the time, but it was probably a mixture of these games that really were the thing that landed it in the end. So Mario 64 came out in September of 96. Tomb Raider was October of 96, and Quake was June of 96. Now, that really kind of solidified what polygonal 3D games should really look like in the marketplace. So Sega Saturn had shipped with home ports of Virtua Fighter and Virtua Racing in 1994, but the release of the PlayStation and the N64 kind of set the scene for those first games that felt like you were really in a 3D world. Now, there were plenty of other games doing 3D between 1994 and 1996, but it's easy to remember it's easy to forget just how ropey some of this stuff really was. Game design conventions were new, control schemes were really, really not very good. And, these games really locked down some of those conventions here. Things like 3D camera control, which, was honestly a puzzle that probably kept on giving all the way till about 1999, 2000. Really, Mario 64 was the first game to get it right. Of the three, I reckon Tomb Raider has probably aged the worst due to some really unfortunate tank controls. I don't know if anyone's played the original version of Tomb Raider, but it really is exceptionally, exceptionally difficult, and you have to play it on a grid. There was a remake this year, actually, where they did patch in modern controls, and you can now play Tomb Raider 1 without it being like the hardest game you've ever tried to play. Mario 64, Quake still hold up, to be honest. Like, I think of the three of them, Quake probably had a bigger influence, but Mario 64's game design is timeless and still feels good today. The other interesting thing Quake did is it pioneered 3D multiplayer. Now, so a quick recap before we go on. So we've talked about three ways of simulating 3D through early video game arcade implementations. So there was vector line drawing that projected 3D into early orthographic projections, which rendered isometric viewpoints. And we had sprite scaling that simulated 3D models rather than using polygons and then finally true polygons. But we've not really talked very much about speed or performance or the home computer market, where a lot of this work started happening. So there's this kind of weird parallel thread in the development of video games. And it runs basically from the 90s and the 386 and the IBM PC. So the PC kind of existed in this alternate parallel universe from games consoles as the time, like the two things really didn't meet in the middle. The IBM PC, as it standardized in the early 80s, wasn't really seen as a thing of play. It was something that existed in home offices. So games were written for the Commodore 64 or the Atari in the UK scene, or games consoles in the Japanese scene. And at the tail end of the 1980s, especially with all this kind of development happening, PC users started to slowly exist in the home, right? As people were using PCs at work, and they were very, very expensive, but there were slowly games starting to be written for them. But the kind of games you expected to play on PC were very unreal time, point and click, early LucasArts adventure games, narrative or text-based, just very, very slow, low fidelity games. So famously, like the biggest selling games of the 80s were things like King's Quest, Elite, Lode Runner, and Zork. I mean, at least one of those is literally a text adventure. So basically, the market wanted Mario and Sonic, and all the PC had was clicky mouse games. Until I'm going to tell you about Gabe. It's secretly really impressive. So in 1991, a company called Softdisk put out a game called Hovertank 3D. Anyone ever heard of this? No, there's next to no chance you've ever played it. So it was part of their Gamer's Edge series of monthly cover discs that they were put in front of magazines to sell magazine copies as free games. That was it. And the Gamer's Edge series of monthly discs were curated by a man called John Romero. So Softdisk have made a name for themselves as part of what became the shareware scene at the time. It was like the very start of the idea of shareware. And this was one of the many games they put out, just like any others. And it's described like this. Let me get this description. This is wonderful. Hovertank 3D, set during a nuclear war. The player controls Brick Sledge, a mercenary hired by an unknown organization referred to as only the UFA, to rescue people from cities under the threat of nuclear attack, largely both political activists or scientists, both by the government and by large corporations. However, the cities are also full of mutated humans, strange creatures, armed guards, and enemy hover tanks. Not really the narrative kind of arc that you would expect from a game in 2024, but I don't know, I kind of like the idea of playing as Brick Sledge. It sounds like it could have been anything, right? However, Hovertank 3D was a lot more important than that. And the reason Hovertank 3D was important is because these were the people that built it. So the four people that were working on the Gamer's Edge cover discs at the time were John Carmack, John Romero, Adrian Carmack, no relation, and Tom Hall. So these people would go on to be the four founders of the prolific video game studio id Software. Originally, it stood for Ideas from the Deep. That was the original name. And these are all, I love the 1990s school family photos. Like you can imagine the photographer who made them pose for this thing on each other's laps. Great. And in their evenings, while they were working at Softdisk on these cover-mounted CDs, what they were actually doing was they were taking their work computers home in the trunks of their cars in Texas somewhere, I think, at the time, and working on the games that would later become the famous games that id Software brought out. Now, why is this interesting? This. Anyone seen this screenshot before, you reckon? But specifically this screenshot. So the team really, 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 really liked the Nintendo, the original Nintendo Entertainment System. And they were convinced they could build console fast graphics on a PC. So what they did is they ripped off Mario Brothers 3. So this is not, in fact, a screenshot of the real Super Mario Brothers 3 game. This is an id Software bootleg clone of Mario Brothers 3. At the time, everybody in the world thought that was impossible. Nobody thought they could write an engine that would go fast enough on PC hardware to provide smooth scrolling in 2D. So basically, the NES was really impressive for 1990. And what they did is they sat with tracing paper over a monitor and they traced all the sprites and built a 2D engine to clone the game. And they thought, oh god, let's license this game from Nintendo. We can bring it out on PC. Everyone's going to love it. And they sent a copy to Nintendo, who told them to fuck off, which is really what Nintendo do to everyone to this day if you ever ask them to license their IP. So yeah, Nintendo politely declined the port and told them they couldn't use it. And what happened then is they built a game called Commander Keen, a 2D side-scrolling platformer where you jump on things on the PC that ran really fast. Funny how that happens. Not at all suspicious. So in another world, Super Mario Brothers 3 might have been released on the PC, and we may have never played Doom. That's a thing that could have happened. So Hovertank 3D was the game that they built to follow Commander Keen, and was their first ever 3D engine. And it took about 6 weeks to build, and compared to other pseudo 3D engines at the time, it actually was fast enough that you could play it. Now, it was the game engine that would then form the basis and the prototype for the Wolfenstein 3D engine, which would later become the foundation of the engine behind the game Doom. It then went on to develop Quake, their first foray into true 3D rather than just sprite map projection mapping, and its sequels, Rage, and the various modern Doom games, and all sorts of other stuff. Carmack eventually would serve as CTO of Oculus Rift at Meta. He got really into VR. I think he got into amateur rocketry as well. He's now doing AGI research because John Carmack. So these games were renowned for their speed, and it's what made them really, really playable and what made them really famous and addictive, along with pioneering online multiplayer. You know, there are many, many stories about how university networks were crashed in 1993 by the shareware version of Doom. So part of the reason that these games ran so well, though, was because of how the graphics engines worked and because of the hardware constraints. The engines worked around the hardware constraints at the time. So Doom used a technique called BSP, binary space partitioning, in its map data, and that helps the rendering go very, very quickly. But we're not going to start there because BSP is a little bit more confusing. We're going to start with Wolfenstein 3D and how its renderer works. So if you're interested in more information about this, there's a narrativized history book on id Software. Came out in 2003. John Carmack just released a biography, Carmack Romero, this year called Doom Guy, which is a really good read. You learn a bit more about his sex life than you might want to read. I will tell you that for a fact, but it's a good read and he's a lovely man. Good story about the origins of all this stuff. So let's talk about making things fast in 3D. There are only two things you need to know about making things run fast in 3D. Render as little as possible and do maths really quickly, honestly. I half joke, but it's basically as true in 2024 as it was in 1991. So the games industry today is full of really, really clever optimization techniques to work out how to maximize what you do not draw. If you ever see any debug views in current games, you will realize that basically the only bit of the 3D world they're ever drawing is exactly the thing that you're looking at. And there's some really fun like camera hacks you can do where you can see all the world around you unload as you're like walking through an empty room in the dark with a torch showing you what should really be there. It's quite fun. But what we're going to look at today is a technique called raycasting, which was the basis of both Hovertank 3D and Wolfenstein 3D's original game engine. And it was an early approach to make things run really, really fast. So raycasting is the use of ray surface intersection tests, it's a mouthful, to solve a variety of problems in 3D computer graphics and computational geometry. The term was first used in relation to computer graphics in 1982 by a guy called Scott Roth to describe a method for rendering constructive solid geometry models, which is exactly what university researchers write about, right? Thanks, Wikipedia. So Wolf 3D uses raycasting to convert a 2D level design, a flat maze, so this is an actual Wolfenstein 3D level, into a 3D projection. And we're going to dissect and clone this behavior. So it's funny because where we started really was how do we convert 2D things into 3D space, and it's just a projection of this. So how do we do that? So I've drawn a very, very crude map on this slide. This is a top-down map. It's a big empty room, 2 big blocks in the middle of it. I'm going to win a BAFTA for game design. Towards the bottom of the map, there's a circle. That circle represents our camera facing north. Now, if we were to imagine that that camera was casting rays, drawing straight lines from every part of its field of view, it might look something like the lines drawn here, but there'd be lots more of them, right? So the number of rays that we're casting here isn't really that important, but in a real worked example, it would relate to the focal length of the camera that we are simulating. So the further a ray has to travel from its origin before it makes contact with something, the further away that thing is, so the smaller it looks. Now, I'm going to use 8 rays as an example here. So we're going to take this and we're going to project it front on. So imagine that we record the distance each of our rays travels, and we fill up a column. The further a ray travels, the fewer pixels we fill up in the column. Kind of looks a little bit like this. So our first ray was really close to the left-hand block, and you can see it up in the top left. So we're filling up lots and lots of pixels because it's really close. The second ray is clipping the side of our left-hand block. So again, we fill up quite a few pixels, but a little bit less than the first ray. And now the third through 6 rays are shooting off into the distance before they make contact with the surface. So we fill in only a few because they're all the way at the end there. Now, once we reach our 7th and 8th rays, we're kind of making contact with the box on the right there. And so we're filling up more of those columns again. Now, this, when represented in this way, doesn't look like much. It's just we're filling up some columns. But here's one single neat magic trick. If we center the pixels vertically, actually what we have there is a very, very low resolution image of that 2D space. Right, so with this one simple trick. So we have to make sure, obviously, that the same amount of space is equally divided above and below our pixels. But suddenly we actually have a projection of that 3D world. And with a wall in the far distance and some blocks to our left and right, this is fundamentally all ray casting is doing. Now, what you do is you shoot a number of rays from the left to the right, and measure the distance. If the surface is solid, the ray stops. If the surface isn't, they can continue to travel until they reach other surfaces. Now, this approach is faster than other rendering techniques that order objects from their Z-index. So early Proto 3D games would draw back to front. So you take all the pixels in the background and you draw again over the stuff in the foreground and again for the character sprites. So you waste all of that computation by repeatedly repainting. And this approach, while working, you can kind of see how it would multiply out. So basically, that's the maths. I didn't do an A level in maths or any of this. So what we do is we set a max range on our camera, right? So our rays simply give up if they're too far in the distance. You might remember early 3D games having like a fog of war. That's when the camera gave up. And now we can now express the number of pixels in any given column as a percentage of that total distance, right? So we calculate the percentage of vertical pixels to fill up any of the columns, divided by the camera range, and we just times it by 100 to make the image bigger, right? Could use any, like, depending on what you're simulating, that magic 100 could be a different number. So by doing this, all we're really doing is just measuring how far away a point is. And by doing it, we're projecting a 2D space into 3D. So we end up with something that kind of looks like this, if I was to flood fill where the rays actually hit. Now, let's talk about turning this into an actual image. Now, the simplest way is all we need to do is we just cast a single ray for each and every horizontal pixel of our target output image. Right, so while in our worked example, we're only considering 8 rays, it's not really computationally too expensive to cast, say, 1024 rays, or 1920 by 1080 if you were doing ray tracing in a big picture. You get full HD. Now we just single ray for each pixel going across. So let's look at some sample code and see how we could actually implement that in C Sharp. Of course, .NET user group, so kind of gotta show the goods, right? So this is the simplest raycaster I could fit in some slides. Caveats here, there's a couple of bits of scary looking maths. I'm really sorry, I Googled them at the time and then took detailed notes that I don't necessarily remember by heart. So I have to read the hard bits from my notes. So, okay, look at this. This is our glorious 3D game level. Be astounded, 2 cubes in a room. I can, it's a cover shooter, right? Gears of War. So this is just a bog standard file new project .NET console app. And I've added 2 static variables, max camera range, and I'm going to set it to 50, the max number of steps before we give up, and a string array called world. Now, we're going to put our level data in that string array and use my innovative new data storage format. It's called hashes for walls, coming to all the new games. So for the sake of this example, any space has a height of 0 and any wall has a height of 1. That's it. Now you can see how you could extrapolate that out to have half height surfaces and things that rays could pass through. We're also setting up a camera location. That's just this location 2D object at the very bottom, just as an offset in that space. It's just an X and Y coordinate, right? So the camera will be located 10 characters in, 7 rows down in our array, facing right by default. Now, our array is a list of sample points, and a sample point has a location that it's sampling, and it stores the length of the array up to that point. So every step that we walk, we just basically have a list of points that we move through. And then array has a length at the end, a total distance that it's traveled. The idea is that we'll just write code to walk through our map, and we'll append the sample point to this list as we go. And the final one in the list connects with a surface. You'll notice that we have a property in the sample point called surface. In our map, I said before, we only have 2 kinds, nothing and a wall, but it could be anything if you wanted to expand that to be more useful. Now, this is basically the hard bit, one of the 2 hard bits. There's a lot going on here, so I'm going to go through it really, really slowly. So we're going to create a new result, which is an array of sample points for exactly the width of our desired target image. And remember, each horizontal pixel needs array casting. We're then going to perform a for loop for each pixel in our targeted horizontal resolution and shoot array. Now we work out our X value, which is the angle of the ray we want to cast, by taking our column number, dividing by the render width and subtracting 0.5. This effectively takes our desired camera angle and splits it into columns. So we're adjusting where we shoot each ray a little bit each time. And then we create our origin sample point at the location where our camera is placed. We're then going to work out which direction to cast our ray. Now, this is one of those maths things that if you weren't paying attention in school, you definitely don't remember. And don't worry, I had to look this up again at like the age of 38 years old. So a radian, anyone know what a radian is? Cool, we've got half the room. There we go, smarter than me. Is a standard unit of angular measure that describes how many degrees around a full circle that you are. And I read that, I was like, wow, that's a really, really fancy word for degrees around a circle, but who knows. So the direction in degrees that we want to cast is our array is pi over 180 times our camera direction plus the additional camera offset. That's the little bit of secret sauce. And then we return a cast direction object created from our direction, which is a number of degrees. Now, a little bit more maths that you might have been sleeping through in high school. Our cast direction object contains the sine and the cosine of the direction we provided that is expressed in radians. Now, remember, radians are just what direction around the circle we're pointing. Sine and cosine are the 2 main functions of trigonometry, and they calculate the ratio of sides of a right angle triangle. So in our case, they're going to help us work out how far left and right we're going to start casting our rays from that initial focal point. Now, this is the core of the ray casting implementation, and it kind of looks really ugly. So we loop forwards, walking 1 step forwards, following the shortest path the ray can take. We do this by using the sine and cosine along with the current X and Y calculated, but to work out the next logical step forward in a given direction. So camera pointing that way, here's X and Y. What are the next coordinates? What are the next coordinates? We compare the length of each step, choosing the shortest path. And once we know which it is, we call the function inspect, telling it to either shift 1x or 1y. So we're basically going in a jagged path through our array, through our 2D array, following whichever step is the shortest each time. So inspect then returns a sample point, and that basically says, hey, I got this far and I hit something. So if the next step has no height, cool, we just add another one and continue onwards. And if we reach something with a height, we store that sample point and we return our completed trace path. So we end up with a list of rays with lengths. Working out the next step is this little piece of maths here. So what it does is when given an angle in degrees and a pair of coordinates, it calculates the next step forward along the line. Now it feels really mathsy, and it was certainly an eyeful when I first tried working it out. But what we're doing is we're saying to calculate the X next step, take our cosine value called run. And if it's greater than 0, we add 1. And if it's less, we subtract 1. This is then inverted when we call the method for our Y step, which takes the sine value, which is now called run. And if our Y, so our Y either has 1 added or subtracted from it. So we're kind of, it's kind of, not, it's the opposite of taxi cab maths, where you go along the longest path of 2 sides. It's the one that makes you walk through the middle. If the first value is X, we just return that location. If it's Y, we need to flip our X and Y coordinates because we've called the method with our parameters flipped. It's a horrible brain melt. But it's like that much code and it lives in the middle of it and you never have to look at it again. So don't worry too much about it, but this is the canonical way to compute that thing. So our inspect method shifts either X or Y by 1, and it calls detect surface, which converts our double down to an integer, which is then an XY location in our array, and then we just basically check if it's a hash or an empty string. These values are consumed by the loop back in the ray function, which evaluates if this response has collided or not. And in a more comprehensive example, you could do things like detect the surface as being glass. So maybe when you are coloring in your pixels, you put a blue hue over them, or you could detect water and continue traveling. So you can do these kind of compositional rendering tricks. That's kind of fun. Now, after casting our rays, we have this total distance value for each point on our horizontal axis, but we need to do a little bit more work to convert this into an image that might look like something useful. So we split out these two steps to make them a little bit more explicit, but you could merge our cast rays method with a render bitmap function if you really wanted to. Now, you'll see I've got like a bitmap renderer at the bottom here, and it's responsible for taking an array of computed rays and working out how many pixels to fill up each vertical column. We're then writing the bitmap to a memory stream and having it write to disk so I can open it in Windows. Right, take a look at it. So that's basically just this. And all this code does is take a 1024 by 768 resolution, which I passed in. And we're using ImageSharp here, which is an awesome library if you've never used it before. It's a really, really cool open source, pure C# fast image processing library. And we're going to loop around each of these sample points for our column. We're going to take the total height that the column could be. We're going to paint some pixels and then we're going to center them, right? Now, the cool thing is, if I run this, wonderful low res hashes for walls pixel universe. This felt like such a long journey when I first got there, right? I was in the pit for like 4 days reading a couple of maths textbooks to make sure that I was getting the thing right. But you can see really, really obviously how that 2D projection lands here. You know, this is some AAA game design. Love it. So there's a few more things we want to do to make this useful. So we could just obviously gradiate the colors based on distance. So we're going to do some really, really quick back of the envelope maths here. So we're going to treat RGB 200, 200, 200 a glorious off-white color as the maximum brightness that we're going to render. And the further away the wall is from the camera, the dimmer we're going to simulate the surface as being. So we're just going to tweak the values of that RGB value. In a real game engine, obviously based on the surface, the way they work is based on the surface you hit. References a texture file, it goes and it loads the texture file into memory and it finds the pixel that corresponds to that location and it paints the color on the surface. But here, we're just going to say, if you're far away, you're darker. And actually, it's kind of alarming how good that is, given such a low fidelity approach to rendering, right? So we got a black and white image that represents our string array map rendered into 3D with our own raycaster. Bruh. So I'm going to show you one more nice hack for success. See this gradient? I like this gradient very much. I made it in 2 minutes in paint.net, and it might not seem like much, but it's my gradient. And the reason I love this gradient is I can use it to cheat, completely use it to cheat. And I can use this gradient to provide additional texturing to the floor and ceiling of the raycaster with no extra effort. And this is exactly what Wolfenstein 3D did. There is no floor and ceiling in Wolfenstein 3D. So instead of creating our own world from a blank image, we just load this gradient onto our bitmap ahead of time, right? This is super sneaky because makes it look like I've actually done extra work, but it's just a gradient on the image first. The truth is, this is a screenshot, obviously, of a slightly higher resolution render, and I changed the focal length of the camera so you can kind of see it out in the wide. I made this playable. So this is a screenshot of the playable version of this that I crammed into a Windows Forms UI in a bitmap box. It's literally a picture box control, and all I do is on a timer every 60 seconds, I load the image. That's it. It's good enough to demo, to be honest. Wiring up controls in WinForms obviously is super, super simple, and just subscribing to like on key down events. So I have this model in memory that controls my camera location, and when they press a button, I just shift the number a little bit. That's it. And then the timer ticks and updates the picture on the control. I think I spent 15 minutes doing that in total. Like the control scheme for the game was 15 minutes of work. And also, just for a laugh, I also cut and pasted all the code into a Blazor app, and it worked first time, which I thought was quite funny. So you could actually, in real time, edit the level and hit submit, and it was re-rendering the screen. So I thought that was all kind of pretty fun. I just did that to see if it would just work. Obviously, there are plenty more places you can take this approach and this kind of idea. So obviously, we're missing texture mapping. So you could add texture mapping, like I said before, where you have each of your surfaces corresponds to a particular texture, and you look up the offset of the picture and you position it on the color, and that's literally just reading color values and painting them. We could implement glass, half-height walls. Also, the code is absolutely not performance optimized, and realistically, it's not the kind of thing you would write if you were going to build a 3D game yourself. But to me, it's an interesting curiosity, and I had a lot of fun doing it. And I think that the truth is, it's nice to see that the languages that we have today are still capable of doing this kind of stuff. And actually, it's so much easier than it used to be. So if you want to build games in C# today, use Unity or Unreal Engine with the C# bindings, or Godot with the C# bindings, or Monogame. But I hope this has been a little bit of a fun story as to how I got there. This link probably doesn't work, but the code is on my GitHub if you Google me. Just one note before we finish, though. The first couple of times I did this talk, everyone said, "Is this the same as ray tracing?" And kinda. So this is ray casting, but ray tracing, like your modern NVIDIA GTX 4090 Big Bastard Edition that costs £2,000, is kind of doing the same thing, actually. And at one point, ray casting and ray tracing were used interchangeably throughout history. But when you hear ray tracing today, what they're really doing is shooting rays of light through 3D spaces. And instead of using it to do projection, they tend to be using it to simulate lighting So they're bouncing those rays off multiple surfaces and reading the simulated values of what basically the blend of colors and lighting effects they transfer through to get much more realistic physical simulations. So yes, but also it's probably doesn't look anything like that when they're actually doing it on an RTX card. Actually, what a lot of modern ray tracing does to get us over this hump of performance, because it's really, really expensive, is they do subsampling. So they take a version of the image, they shrink it down to like 800 by 600. They do the ray tracing in the small image, and then they do AI upscaling of the lighting effects and map it back over the image on the top to be able to do this kind of thing that's computationally kind of expensive at 4K resolution for everybody else. If you're interested in seeing how some of that stuff works, there's some really interesting teardowns on YouTube of the Quake 2 RTX port that NVIDIA did, where they backfilled RTX ray tracing into a modified Quake engine. So I want to leave you with this really, really small anecdote about a question I had when I was 10 years old. And so I played Doom on a 486 without a DX coprocessor, like a shitty old 486. And my 486 couldn't run Doom well. It was really, really slow. And one of the options to make Doom run faster is you could reduce the size of the window by tapping minus on the keyboard. And the smaller the window got, the faster Doom got. And I couldn't work it out. And then later, I played a lot of Doom on the 32X. You know, I don't know if anyone remembers the Mega Drive plugin that like 10 people bought and cost like 200 quid, and they discontinued in 6 months. But there was a port of Doom to it that was pretty good. And it too rendered in a bordered window on my Mega Drive. And while I was writing this talk, I realized, of course, that it's because there's less pixels to render. And Doom's BSP engine, whilst not being a raycaster, could similarly reduce where it was pulling for by shrinking the pictures. And that's why Doom went faster when you made it look like a postage stamp. And actually, that kind of blows 10-year-old me's mind, I think, a little bit. So I hope this has maybe inspired you to do fun things that you don't have to get paid doing, because why not? Honestly, it's much more fun that way. Nice. Thank you. And almost exactly on the hour. Now I'm going to stop sharing and bring back all the faces of the people on the talking on the screen in case they are saying anything. No, Zoom. No, you don't agree? Yeah, Pete's gone to get pizza. And I fear that if I unmute something here, I don't know, I can see people smiling in the other places. I presume you could hear me through that whole thing, right? Big thumbs up. Amazing. Thank God, because that would have been really, really awkward if it wasn't working. And I'd just kind of done it for an hour instead.
I was sitting here kind of hoping that you were going
okay,
to.
so I can see
Oh,
someone speaking on the screen, but I can't hear them, which is really interesting.
That'll be me.
Not muted.
That'll be me.
No. Let's see if they are or not. Great question. There we go. Try again.
I was sitting here kind of hoping that you were.
Okay, but this is that thing, isn't it, where Zoom's configuration is probably using the HDMI. So I'm going to go in here to settings and. Okay, where has Zoom moved all the shit to? Need technical support. Okay, audio down here in the bottom. There we go. Speakers. Same. How weird. Muted. There we go. And unmuted. Hello.
Hello.
There we go. You're finally live after all that. Did that all come out at home? Sorry if you got to see.
It did, yeah.
Yeah, it came out great, David.
It's good to see you guys.
I was sitting here kind of hoping that you were going to cover Euclidean geometry and things like that.
Anyone else heard that term? It's super interesting. Euclidean geometry and non-Euclidean. Have you ever seen? There's a really great series of demos. God, what's that fucking game that came out recently? Superliminal. Yeah. Have you played that?
No, I haven't. I've heard of it though.
It's so good if you want to see a good example of what happens when games break. So Euclidean geometry is the normal world, right? Everything kind of looks like a shape that it looks like from the perspective you see it.
Yep.
Non-Euclidean geometry is where you walk into a four-roomed box, and every corner you turn, there is more corners because your perspective is manipulated and you're kind of shifted into geometry that does not fit in the physical space that you perceive it to fit inside of. It's an absolute brain melt, and I wonder, what do I have in my browser? It's my work laptop, so it could be anything comes up here. I bet YouTube's blocked for fun. YouTube? No. It might work here. It might not work on my computer. There's a really, really great video though. You're just going to see all my weird YouTube searches. Non-Euclidean geometry demo. This is really, really cool.
Really, depending. So I'll just show you some of the things it can do before I go into how it works. First example is this tunnel. You can see it's really long from the outside, but it's actually really short on the inside.
Absolute brain melt. Hate it. Great.
And then this tunnel is the opposite. It appears short, but it takes a long time to travel through it. The shortest path between 2 points is not necessarily a straight line anymore. Here's another example of a house. See if you notice anything suspicious as I walk through it. Did you catch it? This 4-room house actually only has 3 rooms: red, green, and blue. This demo surprised me a lot because I originally thought it would be super jarring, but actually everyone I show this to doesn't notice it at all unless I tell them that something is off. I guess our brains just aren't used to thinking this way. Here's the same house, but with the opposite twist. There's actually 6 rooms in this house. And in fact, I could cram an infinite amount of space into any finite space.
Yeah, so this stuff's really fun if you ever want to play with it. But yeah, there's a game called Superliminal that every puzzle in the game is something like that. Like you reach through the window and you realize you're plucking the moon out of the sky, and the moon's actually the size of a ball in your hand, and it melts your brain. Very good.
Back in the 1990s, the first ever bit of 3D graphics I ever did as a teenager was to write, I wouldn't call it a 3D engine, but it was a 3D graphics kit of BBC basic procedures that allowed you to do 3D on a 2D screen on a 32K BBC B micro. And I used Euclidean geometry for all of it.
That's kind of amazing. On the BBC Micro?
Yep, on the BBC Micro.
Definitely better than Maths and Iron. Awesome. Well, that's basically all I got. I have another tour from Game Engines that's all 2D and much easier to understand, but maybe I'll do another time.
Well, one thing I would say to anybody who's interested in what David was talking about, the book you really, really want to be reading is The Big Black Book of Graphics Programming by Michael Arbrish.
Yeah.
It is an absolutely fantastic book. It puts War and Peace to shame, but the level and depth of the technical details in it to do with rasterizing on early CGA, EJ, and VGA systems is just outstanding. It's mind-boggling, but it's outstanding.
And in fact, Michael Arbrish went on to work at id Software while they were working on Quake, for that reason.
Well, I think it was either John Romero or
Mark hired him because he read the book and was like, you've solved all the problems I'm trying to solve. Look, come work with me.
Up here behind me, I actually have, you probably can't see it on camera, but I've got a first edition there.
First edition. It's terrifying.
And then next to that, I've got Game Code Complete, which is the second edition, which takes a lot of the lessons learned in the Big Black Book of Graphics Programming and applies them to C language and the early days of OpenGL. Again, another very, very good book. I think that was a Something Press one. Can't remember the name of the publisher, but certainly I started my programming career writing games. And they were the things that really broke the barrier for me, learning all the maths.
You say you did BBC Micro. Where did you go after them though? Because there's obviously like a leap between like the microcomputer era and DOS.
So after the BBC Micro, I stayed with the Acorn line and I went on to work on the Acorn Archimedes series. 3000, the 5000, and I worked on a lot of the game conversions from the Amiga and the Atari ST across to the Acorn platform.
Awesome. I'm kind of jealous. Feel like I was basically 5 years too young to do all the fun bits of game programming. So, like just too young.
There's the man there, Peter. You've seen my Archie demos, haven't you?
I have. We're just like time.
I did quite a lot of stuff on the demo scene as well, David.
That's right. Yeah. And with I think Vulkan,
Yeah.
you can do GPU stuff and blend it with the actual graphics.
And Vulkan's really interesting in that people keep trying to make Vulkan happen, but the console standards, basically DirectX is so powerful, and the games consoles are so ubiquitous that like I don't know whether I think Vulkan will win.
Well, they're going up against CUDA.
Right.
And NVIDIA.
And the might of NVIDIA, yeah.
NVIDIA's got more money than open source.
Than anyone.
Yes.
Aren't NVIDIA now the richest company in the world or something stupid like that? Well, they were for a month,
Yeah.
but that's a lot of money.
It's value. It's different from virtual.
I've got to confess, I've not done anything with Vulkan itself, like the Vulkan API. The last time I actually did anything really serious was still with OpenGL, so I'm not too clear on the differences between it. If anybody wants to...
Vulkan blends OpenGL and OpenCL, because like you, I did a whole load of stuff in OpenGL and a lot of it in OpenCL. And then just as I was kind of putting everything to bed, go and do something actually valuable with a
Boring job.
They brought out Vulkan and I realized they solved a lot of the interrupt problems I was having. And tried to switch the context between OpenGL and OpenCL and back and forth. So one computes what should be shown, the other one actually displays it.
And you got to talk for another day. Right, I can smell pizzas.
Yes, hold on, yep. Right, we'll disconnect Whitney. Oh, there we go. Almost. You'd be able to just go ahead and disconnect from the whole session if you want.
We'll work that out now.
Or mute, whichever. Oh, that's better. Cool. So thanks very much for coming, folks. I'll turn my video around so you're not staring at the floor. There we go. And thanks for the in-person folks have got pizza thanks to Rebel Recruiters, and they've also got no rain on their head thanks to BGSS. So thanks to them. Don't forget to tweet on that hashtag .NETNots as well if you want a good chance of winning a JetBrains license. Even if you don't actually need one, you can give it away to somebody else. So do that. Thanks, obviously, to our wonderful speaker, David Whitney.
Thank you.
Applause. Yeah,
Appreciate it.
it's good. And thank you for coming all that way as well, because it's not 2 minutes.
Mate, you have no idea how chaotic today has been.
We'll find out. So yeah, and next month, hopefully, maybe we'll have Connell, something like that. In a week or so, don't forget Knots IoT, and a week and a bit Latty as well. So do go check all of that lot out, and we'll